On August 6, 2025, the James Webb Space Telescope aimed at a brand new interstellar visitor, Comet 3 I/ATLAS. And what Webb saw wasn't a photo. It was a chemical fingerprint. And that fingerprint said something that, for a comet, is borderline ridiculous. This thing is pumping out carbon dioxide, while water, the usual star of the show, is barely showing up. The CO2 to water ratio from Webb's spectra comes out to about 8:1. Read that again, 8:1. That's not interesting. That's your baseline assumptions just cracked interesting. And it's why people started saying astronomers were panicking. But here's what that really means. They're not panicking because they think it's aliens. They're panicking because this discovery might change how we interpret every interstellar object we ever catch. Because there's a very uncomfortable possibility hiding inside this data. What if 3I/ATLAS isn't a pristine time capsule from another solar system? What if it's a relic that's been chemically rewritten by billions of years of space radiation? And Webb just caught it mid-confession? By the end of this video, you'll understand what Webb detected, why that's a huge discovery, and what the one detail is that could change everything about how we read interstellar visitors. Quick context. 3I/ATLAS is only the third confirmed object we've ever seen enter our solar system from another star. The first was Oumuamua in 2017, the one that started 1,000 arguments. The second was 2I/Borisov in 2019, the one that looked and behaved like a very normal comet. Then, on July 1st, 2025, the NASA-funded Atlas survey in Chile flagged another fast-moving speck. It was moving too fast to be bound to the sun, a true fly-through. NASA puts it at about 137,000 miles per hour when discovered, accelerating to about 153,000 miles per hour near perihelion. And no, it's not a threat. At its closest, it stays roughly 170 million miles away from Earth, so you can breathe. But you should also lean in, because we almost never get a sample from another star system we can study in real time. This thing formed around a different star, in a different protoplanetary disk, with a different chemical recipe. Then it got kicked into interstellar space and drifted for who knows how long. And now it's here. One pass, one chance. Which is why every major telescope that could possibly look at it did. Why Webb looked, and what Webb detects. Webb is famous for galaxies, but it's also one of the best chemical instruments humanity has ever launched. It uses spectroscopy, splitting light into a molecular barcode. CO2 has a signature, water has a signature, carbon monoxide has a signature. Even rare sulfur molecules can show up. It's like hearing a song through a wall and identifying the instruments. You can't see the band, but you can tell what's playing. On August 6th, 2025, Webb used NIRSPEC, the near-infrared spectrograph, to look at the coma around 3I/ATLAS in infrared. And the first big result was simple. Carbon dioxide dominates. Now, if you're thinking, wait, comets are mostly water ice, right? Yes. That's what makes this so weird. What Webb found, the 8:1 problem. Webb's team identified carbon dioxide, water vapor, carbon monoxide, water ice grains, dust, and even a tentative hint of a sulfur-bearing molecule called carbonyl sulfide. But the headline is the ratio. The CO2 to water mixing ratio is about 7.6:1, basically 8:1. And it's not just high, it's high in a very specific way. Because at the comet's distance from the sun during Webb's observation, a little over 3 astronomical units, most comets follow a rough pattern. They can be dusty, they can be gassy, they can be weird. But the CO2 to water ratio usually doesn't jump this far off the curve. The researchers estimate this ratio is about 18 times higher than what the normal trend predicts, and roughly 4.5 sigma above that trend. In normal language, you don't get this result by accident. You don't get it by a little noise. You get it because something about this object is actually different. And here's a small detail most headlines skip. Webb didn't just say CO2 exists. It mapped where the CO2 is in the coma, and it's not symmetrical. The outgassing is enhanced in the sunward direction. That matters because it hints at how the comet is venting and what might be driving the activity in the first place. Now, to make this feel real in your head, here's the scale. Based on the production rates in the analysis, the whole coma is releasing on the order of about 124 kilograms of CO2 every second, but only around 6 to 7 kilograms of water vapor per second. So if you imagine a classic comet as a snowball that breathes water when it warms up, 3I/ATLAS is more like a snowball that's breathing soda gas. And that's why astronomers got that cold sweat feeling, because the next question is unavoidable. Why? The only other outlier moment. The team points out something else that's important. There's basically one famous solar system comet that sits way out in this same weird neighborhood, Comet C/2016 R2, and C/2016 R2 is considered one of the strangest comets ever observed because it was loaded with hypervolatiles and didn't behave like your average water-dominated comet. So when 3I/ATLAS shows up with a CO2 signature that's this extreme, it's like the universe handed us a sequel to one of the strangest cases we already know. Except this sequel didn't come from our solar system. It came from somewhere else, which leads to 3 possible explanations. Skeptics checkpoint: what we know versus what we don't. Before we go there, quick checkpoint. Here's what we actually know from the Webb data. 1. The coma is CO2 dominated. 2. The CO2 to water ratio is extremely high. 3. There's CO, water vapor, water ice grains, and dust. 4. The coma shape suggests stronger outgassing in the sunward direction. Here's what we do not know yet. 1. The precise interior composition. 2. Whether water is truly scarce or just not escaping efficiently yet. 3. Whether what we're sampling is original material or heavily altered surface. So when you hear people jump straight to "it's artificial," just remember, weird does not automatically mean not natural. Weird means we need better constraints. And if you like this kind of grounded weirdness, the real science, with the real mystery, you're gonna want to subscribe because this story is still unfolding in real time. Okay, with that said, 3 possible explanations for the CO2 dominance. There are 3 broad explanations, and none of them are boring. 1. It was born different. In a protoplanetary disk, there are ice lines, where different ices can freeze out and survive. Water has a line, CO2 has a line, CO has a line. If 3I/ATLAS formed near the CO2 ice line, or in a region where CO2 ice was abundant, it could start life naturally loaded with CO2 compared to water. That's the cleanest answer. Different birthplace, different recipe. 2. It was cooked. Out in interstellar space, there's no protective bubble like we have here. Galactic cosmic rays hammer the surface for millions or billions of years. And here's the crazy part. Experiments and modeling show that cosmic rays can actually drive chemistry, converting carbon monoxide into carbon dioxide and building up an organic-rich crust. A newer interpretation argues that 3I/ATLAS's extreme CO2 enrichment is direct evidence of that cosmic ray processing, and they estimate the outgassing we see could be sampling only a processed layer, something like 15 to 20 meters deep, never reaching pristine interior material. If that's right, then this object is not a simple time capsule. It's more like a space mummified relic, a body that's been chemically aged by the galaxy itself. And that is a paradigm shift, because it means the first thing we measure on interstellar objects might be their radiation scars, not their birth chemistry. 3. The heat isn't getting in. Water ice needs more heat to sublimate aggressively. CO2 and CO are more volatile. They can turn on earlier, farther out. So if 3I/ATLAS has a crust that insulates the interior, dust, organics, irradiated material, it could suppress water release while CO2 and CO vent first, meaning the water might be there. It's just not activated the way we expect yet. And that's why scientists want follow-up observations over time, to see if the ratios evolve as the comet changes, what panic really looks like. So again, the clickbait version is astronomers are panicking. The real version is astronomers are recalibrating expectations. Because for years, the dream was simple. Catch an interstellar object, read its chemistry, learn what other star systems build. But if cosmic rays can rewrite surface chemistry over billions of years, then the coma we measure might tell us as much about the journey as the birthplace. That makes interstellar objects more complicated and, honestly, more fascinating. Now, as if the CO2 story wasn't enough, there's another chemical curveball in the 3I/ATLAS saga. Metal. The nickel problem. Metal in a comet coma. Ground-based teams using the European Southern Observatory's Very Large Telescope detected emission lines from atomic nickel in 3I/ATLAS's coma. Nickel. At distances where it's far too cold for the simple metal vaporizes explanation. Even stranger, in some early observations, iron wasn't clearly detected above instrumental limits, meaning the nickel-to-iron ratio looked extreme. Now nickel and iron have been detected in other comets. This isn't never in nature, but the ratio and timing here are what turned heads. A dedicated study reports nickel across multiple epochs, with iron only showing up once the comet got closer than about 2.64 astronomical units, and the nickel-to-iron ratio drops as the comet warms. So what's the leading natural explanation? Not molten metal, chemistry. The authors propose that nickel and iron atoms could be released via volatile metal carbonyls, molecules like nickel-4 carbon monoxide and iron-5 carbon monoxide. These compounds can break down and release metal atoms without needing furnace temperatures. And if you're sitting there thinking, wait, carbonyl, CO, exactly. Now connect the dots. Webb sees significant CO and extreme CO2. Ground telescopes see behavior consistent with metal carbonyl chemistry. That doesn't prove one causes the other, but it does tell you this comet's chemistry is not simple, and that's the real fuel behind the panic. Because when a system breaks your simple explanations, you have two options. You either find a new natural mechanism, or you admit you don't understand it yet. The internet versus the data, and this is the part where the internet does what it always does. Someone reads extreme ratio, someone hears nickel without iron, and suddenly it's alien probe confirmed. But if you want to stay anchored, here's the filter. Webb did not detect a hull. Webb did not detect a signal. Webb did not detect technology. Webb detected molecules and ice in a comet's coma. That's already mind-blowing. The mystery is subtle, and that's why it's powerful. Why these molecules in these proportions from an interstellar visitor? So what did Webb detect that's a huge discovery? Here's the clean answer. Webb detected that 3I/ATLAS's coma is unusually CO2-rich, with a CO2 to water ratio around 8:1, one of the most extreme values ever measured for a comet at that distance. And the huge discovery isn't just the number, it's the implication. Because that ratio can represent three different things: a birthplace. Other planetary systems can make comets with volatile inventories that look nothing like ours. A journey, the interstellar space can chemically transform objects over billions of years, coating them in processed material and altering what they show us when they outgas. Or a phase, we may have caught this object at a moment where CO2 turns on first and water ramps later, meaning the story evolves over time. Any of those outcomes changes how we interpret interstellar visitors. But the reason 3I/ATLAS is such a big deal is that it hits multiple weird notes at once. CO2 dominance, evidence consistent with heavy processing, and additional odd chemistry like the nickel story. It hints that interstellar objects aren't just visitors, they're survivors. What happens next? The one thing to watch. If you want one simple thing to watch going forward, it's this. Do the ratios change? If water production ramps up dramatically relative to CO2 as the comet evolves, that supports the insulation/delayed activation idea. If CO2 stays dominant and we keep seeing evidence of a processed outer layer, that supports the cosmic ray mummified crust interpretation. And if we see new molecules turn on at different distances, that tells us we're watching layers of the comet activate like a chemical onion. And that's why follow-up matters, because in a weird way, 3I/ATLAS isn't just teaching us about itself. It's teaching us what kind of information interstellar objects can and can't reliably carry. Just a quick recap. Here's the three-sentence version. 1. Webb looked at 3I/ATLAS and found a coma dominated by carbon dioxide. 2. The CO2 to water ratio is roughly 8:1, far above the normal trend for comets at that distance. 3. That ratio could be a fingerprint of the comet's birthplace, or a scar from billions of years of cosmic radiation. And either way, it changes how we read interstellar visitors. Now I want your take. Was 3I/ATLAS born different, or was it transformed? Drop your theory in the comments. And if you want the next update the moment new observations come in, especially if those ratios shift, make sure you're subscribed, because this is one of the rare moments where the universe hands us a sample from another star system, and we only get one pass.